So the first talk is an invited talk given by Dr. Yukako Fujishiro. So let me introduce the speaker briefly. She received her PhD from the University of Tokyo 2021. And after 3 years postdoc at the RIKEN Center for Emergent Matter Science, she has been leading an independent research group at RIKEN since April 2024. She got many awards such as Forbes 30 Under 30 Asia list in 2022, L'Oréal UNESCO for Women in Science Japan Fellowship, and the Dean's Award from the University of Tokyo. So please start your talk when you are ready.
Thank you very much for the introduction. So I will share the slides. Okay. Can you see the slides?
Yes.
Okay, so my name is Yukako Fujishiro, and I'm from RIKEN CEMS in Japan. So today I'd like to share some of the works related to the exotic electromagnetic responses associated with the topological phase transition of topological spin textures in cubic chiral magnets. So especially I would like to introduce the work done under using extreme conditions such as high magnetic field or a high pressure experiments. So these are the contents of my talk. So first of all, I will introduce some of my previous works related to topological phase transition of the magnetic skyrmions, and also a very unusual topological spin texture called hedgehog lattice or emergent monopole lattice. And then I would like to introduce my most recent work related to the pressure-induced metal-to-insulator transition, and also the quantum phase transition of topological spin texture under very high pressure. Okay, so let me start from the first topic. So the topological spin texture, as you may already know, the topological spin textures are now found in various magnetic compounds. And for example, the magnetic skyrmion has a spin texture like this. And when we project these spin textures on a sphere, it actually overlaps one sphere surface and has a quantized solid angle. And depending on the crystal symmetry, we have various kind of detailed winding pattern as shown here. And so the skyrmion is rather a two-dimensional spin texture, while the spin texture called hedgehog and anti-hedgehog lattice has a more three-dimensional nature. And so in addition to this kind of classification, actually the transport measurement is a very important proof to detect the presence of these spin texture. So this is because the finite skyrmion number of this spin texture actually affects the equation of motion in solids. So when the electrons in solids are strongly coupled to the underlying topological spin texture, it acquires a Berry phase, which causes an additional Hall effect called topological Hall effect. So we typically use a Hall effect measurement to detect these spin textures. Okay, and so nowadays there are so many materials where these kind of topological textures are actually experimentally identified. But today I would rather like to focus on a very basic and the most famous material system, which has a chiral crystal structure and hosts a Bloch type as magnetic skyrmions. So the target material belongs to the family called B20 type chiral magnets, B20 type materials. So these materials crystallize in a cubic chiral space group and is composed of a transition metal and also a group 14 element with a 1-to-1 ratio. And it has a left-handed and right-handed crystal structure. So because the inversion symmetry is broken, there's a spin interaction called Jarzynski-Moria interaction, which tries to rotate the spins. And as a result, when there's a competition between ferromagnetic exchange interaction and this Jarzynski-Moria interaction, the magnetic ground state in this family compounds is typically a long-range helical spin structure, where the magnetic period is determined by the ratio of the exchange and the Jarzynski-Moria interaction. And this is the typical generic magnetic phase diagram of these compounds. And as I said, the magnetic ground state is a long-range helical state, where while this very small pocket near transition temperature has a skamion lattice state, which can be described as the superposition of a 3 in-plane helix state. So this kind of skamion texture was first found in manganese silicide, while in iron germanium, which is the target material of the second part of the talk, has a very high transition temperature near room temperature. So it has also been studied very well. And on the other hand, the hedgehog spin texture is found only in manganese germanium with a very short magnetic period. So I'd like to note that the very short magnetic period is very promising, because the emergent magnetic field is inverse proportional to this to the density of the spin texture. So which means if the magnetic period is very short, we might have a large electromagnetic responses from these topological spin textures. Okay. Okay. So, okay. So let me introduce my the first work. So in this work, we explored a transition between two different topological spin textures, which is the conventional skamion lattice in manganese silicide and the hedgehog lattice in manganese germanite, by making a new solid solution, manganese silicon germanium, which was synthesized for the first time using a high pressure synthesis. So this is the phase temperature and magnetic field phase diagram for various compositions. So in the region close to pure manganese silicide, we observed the conventional skamion lattice by using Lorentz stem, by using Lorentz stem. And on the other hand, in a region very close to manganese germanium, we used the neutron scattering experiment to identify the conventional hedgehog lattice states, which was also reported in pure manganese germanium. But very interestingly, in the middle part of the composition region, we found a new topological spin texture using a neutron scattering experiment, which seemed to have 4 Q vectors, which are pointing along the apical direction of the regular tetrahedron. And surprisingly, it had an even shorter magnetic period of 1.9 nanometer. And when we calculate the three-dimensional spin texture, it turned out that it is also a 3-dimensional array of a hedgehog and anti-hedgehog, but the position of these singular spin texture is different compared to the pure manganese germanium. And then we also did a transport measurement to identify the topology of the spin texture, as I just presented before. So in the conventional skamion lattice, we have a negative topological Hall effect, which as shown in this phase diagram. And in the in the conventional hedgehog lattice state, we have a sign change from negative to positive towards the phase boundary state, which is also confirmed in a pure manganese germanium. But in the middle part of the region, we observe a rather unusual sign change of the topological Hall effect from positive to negative, and then again to positive near the transition temperature. So actually, the origin of this sign change is not revealed yet. But one thing we can say is that the spin configuration of these spin textures are different, which really affects the topological Hall effect in this material. So I would say that the transport measurement is again the very important proof for corroborating the presence of topological spin textures. And then we also explore the unwinding process of the emergent magnetic monopole state under the application of magnetic field. So we assume this as 3 Q vectors, which describes the Hedgehog state, and then application of magnetic field. Magnetic field means is adding a uniform magnetization like this. And if we simulate the position of the monopoles and anti-monopoles under magnetic field, we found that there will be a pair annihilation of these spin singularities just before the phase transition. And very interestingly, we discovered that this pair annihilation might enhance the efficient heat and electricity conversion, where we observed a very gigantic magneto-Zivik effect in this manganese germanium. So it is known that the Zivik coefficient has two contributions. One is from the electronic structure, and the another is from the electron scattering. So we actually did a photon emission study to directly evaluate this first term, where we find a very negligibly small Zivik coefficient. When we did a very high magnetic field measurement of the Zivik effect, we found that this giant Zivik effect actually is suppressed in the high magnetic field limit, which means that some kind of spin fluctuation and also the electron scattering is contributing to enhance this Zivik effect in this system. So this is a very unique Zivik effect, which originates from the destruction of the very high density topological spin textures. And another interesting phenomenon we observed in this magnetic monopole system is that in a single crystal thin film, we observed a very large enhancement of the anomalous Hall conductivity. So this is a very famous plot for the anomalous Hall conductivity with various mechanisms, and it typically shows a general scaling relation. But what we find is that this the large anomalous Hall effect observed in this compound largely deviates from the conventional scattering, and we proposed a new mechanism of a skew scattering, where the electrons are scattered from the thermally excited scalar spin chirality. And actually, this model reproduces the giant skew scattering Hall angle of about 20%. So we speculate that this kind of remaining residual scalar spin chirality, which is thermally excited one, is actually present in this high field region and produces this unusual giant skew scattering in this compound. Okay, so let me move on to the next topic about high pressure induced phase transition in iron germanium. So let me briefly talk about the ferromagnetic quantum phase transition in solids. So it is known that tuning the itinerant ferromagnet to the quantum critical point leads to the emergence of the various exotic quantum order. This is because theoretically, in very clean systems, the ferromagnetic quantum critical point is usually avoided, unlike the very genuine anti-ferromagnetic quantum critical point. So the examples here are some very famous examples. For instance, in uranium-based compounds, there is a we have observed the coexistence of ferromagnetism and superconductivity, while in strontium rutinates there also emerges unusual superconductivity or electronematic phase near the quantum phase transition. And very interesting, the manganese silicide, which is where the scandium was first discovered, it has attracted great attention long before the discovery of magnetic scandium. And this compound has been studied in the context of the ferromagnetic quantum phase transition. And in more specific, the unusual exotic magnetic order called partial order state has been discovered under pressure. So the manganese silicide has a TC of about 30 Kelvin, and when we apply pressure, the long-range magnetic texture is completely suppressed at about 1.4 gigapascal, and the non-Fermi liquid state emerges above this quantum critical point. And the neutron group has discovered that there is a unusual short-range spin correlation in this regime, which is strongly dominated by the spin fluctuation on a time scale of 10 to the minus 10 to 10 to the minus 11 seconds. And very interesting, they observe a topological Hall effect in this regime, which usually only appears in the magnetic scandium phase. So from these results, they have named this region a topological non-Fermi liquid state, and they speculate that the liquid-like state of the magnetic scandium is actually formed in this region. So motivated by these works, we have decided to try the similar experiments in iron germanium, which has the same crystal structure, but a very high transition temperature, and it's very famous for the scandium formation near room temperature. And if we apply a pressure to this iron germanium, the system will be effectively tuned to iron silicide because of the lattice change, because of if we consider the chemical pressure between silicon and germanium. And this iron silicide is also is another very famous compound, which is known as a non-magnetic narrow gap semiconductor with very strong electron correlation. So actually in the chemical doped system, this kind of phase diagram is constructed, and indeed they observe a fast order phase transition from the ferromagnetic metal to the non-magnetic insulating state. But because of the impurity of the single crystals, or the very small size of the single crystal they obtained, the very detailed transport measurement has not observed in this system. So we decided to apply a pressure all the way from iron germanium to tune the system to iron silicide and explore if we can obtain a metal to insulator transition, as well as a possible topological non-Fermi liquid state as reported in manganese silicide. And there's one high-pressure previous study on iron germanium using the Mossbauer spectroscopy. So they observe a quantum phase transition near a 19 GPa, and they report that there is some exotic chiral fluctuation state above this quantum phase transition. So, and no one has performed the magnetic transport measurements in this very high pressure regime. So we decided to measure a detailed transport measurement. So I would skip the detail, but we recently built up a measurement setup for diamond ambu cell, which can be measured in PPMS and also optics. And we also performed the synchrotron experiments. And yeah, and so as you already know, it is very difficult to measure precise transport measurement under high fields because the sample size is very small. But we used the very original focused ion beam technique to fabricate the electrode one by one like this and successfully measure the transport using the liquid pressure medium up to very high pressure. Okay, so This is the result. So first of all, we observed the signature of pressure-induced metal to insulator transition. So as you see that when we increase the pressure, the resistivity is enhanced by 2 or 3 orders magnitude. And this behavior is also corroborated by the DFT calculation. And this is very, I would say this is a very rare case because usually the pressure tries to makes the insulator to metal and even superconductivity, but this is the opposite, the other way around, because we are turning the metal to insulator. And this is because the pressure reduces the exchange splitting of the bond structure. And if the Fermi energy is located at the band gap, the system become an insulator. So we observed a very rare case of the pressure in this metal to insulator transition. And then, yeah, this is the phase diagram of the residual resistivity. And you can see that depending on the phase, magnetic phase transition, there is a large jump of the residual resistivity. And this is the magnetic resistance under high pressure. So I'd skip the detail, but most importantly, the very large negative magnetic resistance is observed near the quantum phase transition, which means that the spin fluctuations are actually enhanced in this regime. And this is the Hall resistivity, and you can see that it changes dramatically under application of pressure. And this is a very naive speculation, but according to the DFT calculation, we accidentally found that this kind of topological fermions, which is unique to the chiral system, is actually largely tuned by the pressure and crosses the Fermi energy before the metal to insulator transition. So this actually upturn is due to the emergence of very high mobility, and we speculate that this has some relationship to this Fermi energy tuned topological chiral fermions. But the most mysterious result we accidentally observed is the emergence of the spontaneous anomalous Hall effect near the quantum phase transition. So in the helical or skyrmion systems, they don't have a net magnetization. So we don't have a we don't have a Hall resistance at zero magnetic field. But very unusually, we observe a spontaneous component in this short range magnetic order regime. And generally speaking, the short-range magnetic order cannot break the time reversal symmetry. So this is very unusual. And if we investigate this coercive field change, we found that this coercivity is enhanced at lower temperatures and also towards the quantum phase transition. So we don't know the origin of this anomalous Hall effect, but we speculate that this has some strong relationship to the enhanced quantum quantum fluctuations around this 20 gigapascals. So we're still investigating the origin of this anomalous Hall effect, but because again the breaking of time reversal symmetry without magnetic long-range order is very unusual. So one possibility is the chiral spin liquid state, because the B20 lattice has some extent of the spin geometrical fluctuations, which can generate a degenerate ground state. And another possibility is that if sometimes in a disordered system, the phase called quantum Griffith phase is developed, and they have a glassy and mesoscopic freezing of the spin clusters like this, and this actually breaks the time reversal symmetry, but actually no one proves this state through the detailed transport measurement. So even if this is the case, it might be an interesting scenario for this compound. So finally, I would like to compare the result between the manganese silicide and this time our material, iron germanium. So in manganese silicide, they observe a field-induced topological Hall effect, which suggests the possible liquid state of the magnetic scarmium. But in iron germanium, we observed a very unusual time reversal symmetry breaking in this short range magnetic order state, which is dominated by the chiral fluctuations. Yeah, so these are the summary of my talks, and I would acknowledge the collaborators. Thank you very much.
Thank you very much for the very interesting talk. So now this session is open for Q&A session. So do you have any questions or comments? So if you have, you can unmute your microphone, or you can write on the chat. Okay, so let me ask one short question.
Yes,
So
please.
in the iron germanium, you observe a very large anomalous Hall effect without any magnetic ordering. So if you are using the scaling relationship, can you distinguish the origin of the large anomalous Hall effect?
Yeah, thank you very much for the great comment. So actually, I tried the scaling relationship, but actually it does not follow any of the conventional scaling mechanism, even for the intrinsic mechanism and also the skew scattering, like this, where the whole conductivity is proportional to sigma xx. So I would say that this anomalous Hall effect is not conventional at all, and we need some new theoretical interpretation to understand this phenomenon. Yeah.
Yes. Thank you very much.
Yeah, thank you.
Is there any questions or comments?
I have a small question. Can you hear me? Yeah, I think the hysteresis loop observed at the transition area is very interesting. But I have one question about what's the potential application of this observation, because it seems like it's observed as like two extreme, and yeah, low temperature and also high pressure. Yeah.
Yes. Yeah. So actually, so I think, yeah, as you say that this is very high pressure experiment, but actually we can, if we observe a very interesting phenomena at this pressure, if we can use a chemical substitution method to realize this critical point by synthesis approach, and then maybe we can obtain the same phenomena at ambient pressure. So I think the first doing a very high pressure experiment first is very nice, because we can tune the system very smoothly without introducing any chemical disorder, and find a very intrinsic phenomena first. And then if the phenomena is really interesting, I think making this chemical substituted material would be very important for practical application. Yeah.
Okay, thanks.
Thank you very much.
Is there any other questions or comments? We have a few minutes left. You developed the new system to measure transport in an extreme
Yes.
condition. Is it possible to measure the transport with some annealing or high temperature,
Yes.
along with the high pressure?
Yes. So you mean what high temperature? Like how many?
Maybe above the room temperature.
So we are using a machine called PPMS for transport measurement. And in that case, we can reach 400 Kelvin at maximum. But in general, it is, I mean, there's no limit for the upper temperature for this diamond anvil cell. So we can increase further if we use different apparatus. Yeah.
Thank you.
Yeah.
So do you have any questions or comments?
Can I ask a short a technical question.
Yes.
So I'm interested in this liquid pressure system. So what kind of liquid are you using?
Actually, it could be any kind of liquid pressure medium, but we typically use a Daphne oil or glycerin, yeah, for our experiment.
Okay, thanks.
Thank you.
So we can accept a short one questions. Do you have any questions or comments? I'd like to ask one short question. So the after applying the high pressure, the property is reversible, right?
Yes, reversible.
Ah.
Yes.
I see.
At least up to 20 GPa, we measured the property again when we turned back to the ambient pressure, and it was the same as the original. Yeah.
I see. So do you have any other questions or comments? If not, I would like to thank the speaker. So thank you very much for your
Thank you very much.
presentation.